My name's Jeremy Allison with Google's Open Source Program Office. I'm actually substituting for Leslie Hawthorne, who can't be here tonight, which means, unfortunately, I'm going to have to miss the talk, which is a real pain, because I think I might really enjoy this one. So just a couple of questions first. How did people find out about this talk? Did find it by, I think it was on Google Code blog or something? How many internal Google people are there here? Oh, quite a few. So the non-Googlers, did you find out about it on the Google Code blog? Raise your hands. Oh, one. Okay. We need to advertise more, I think. Anyway, this is a series of talks. It will be going up on Google Video, probably in a week or so's time. So if you really enjoy it and you have friends who missed it, they can always tune into the video. Anyway, so I'd like to introduce our speaker tonight, who's Alex Martelli. And Alex works as an Uber tech lead. I don't quite know what that is, but sounds very important. Uber tech lead for production systems at Google. That is very important. He wrote Python in a Nutshell and co-edited the Python cookbook, both of which I have. So I should have brought them for you to sign. And he's a member of the Python Software Foundation and won the 2002 Activators Choice Award and the 2006 Frank Willison Memorial Award. Anyway, please welcome Alex Martelli.
Thank you. Thank you, everybody, and welcome. So this talk is a very brief introduction to the Python language and a mention of its few libraries for people who are already experienced programmer in some other language. That is the summary. So if this doesn't describe you, if you already know Python very well, or if you don't know programming at all, I will not be offended if you leave. So essentially, I'd like to have here very experienced programmer in some widespread language, such as C++ or Java or C. No need for any previous exposure to Python. If you have some, it won't hurt. If you have a lot, you'll be rather bored tonight. You must be kind of prepared for me to be very fast in some of the parts. Others will be more relaxed, but a few hard stuff I'll be hand-waving a lot about. And I apologize in advance. I have a lot of slides with code example to squeeze more code per slide. My formatting isn't exactly elegant, and some of my names are too short. I don't do that unless you have to code on slides, of course. So what's Python? You probably heard about it, but let's summarize. It's a very high-level language. I put that in double quote because it's a technical term. Low-level language is assembler. High-level language is C or Java. Very high-level language is Python, Ruby, Perl. It's basically got more power per line of code you write, essentially. It takes you far away from the machine, which has disadvantages, but it makes you more productive in coding. The syntax is particularly notable as clean and spare, as we'll see comparing it with other languages. The semantics, we have striven to keep very regular, meaning simple and powerful at the same time and without a lot of special cases and exceptions. For example, we don't have two types of integers depending on whether it's a real integer or an object integer. That's a typical Java or C# issue. Like C, we have integer. That's much simpler. It's object-oriented, but also suitable for other paradigms of programming. We'll contrast that with, compare and contrast with other languages to help you cite it. Its main focus is on the productivity of the programmer. We want the programmer to be able to do a lot of work fast. How do we do that? Well, maybe I'm not using the right order here, because number one is simplicity. Simplicity is the best feature of any complex design. As Saint-Exupéry, best known as the author of the novel The Little Prince, but actually a strong aeronautic engineer, said, you know you've reached perfection in design, not when there's nothing to add, but when there's nothing to take away. Now, Python isn't exactly that perfect, but we're going to take away a lot of things very soon in Python 3000, which you can expect to see out in less than a year. So far, we haven't been able to take away anything once it was in because of the well-known demon known as backwards compatibility. The life of a new language or a new company or a new anything is always easier because you have no customers, and therefore there is no problem with offending your customers. But as soon as you have a few million people using the language or buying products from the company, you can't really be too innovative, except on major releases, and Python will have its first major release in a decade this very year. We'll take away a lot of the things I explain now because they're not strictly needed. Uniformity is another strong Python value. We'll come back to it, but basically the dream is that things work the same way in different contexts. So you don't have to remember a combinatorial complexity of explosion of rules of, okay, how does this work in this case versus that case? Modularity is very important, of course, and pragmatism is engineers' rule number one. All of these theoretical considerations are absolutely crucial, but pragmatism trumps them all. Sometimes something is just too important to not have. It's got a rich standard library, maybe not by Java standards, but pretty rich compared with most other languages, and lots of third-party tools, additions, extensions, and so on. And it's got several good implementations. The one most people think about when they say Python is known as CPython for classic Python. There's also an implementation which was just released as a result of a 2-year project financed by the European community known as PyPy, which is basically Python implemented in Python itself. There's IronPython, which has just released 1.1 and is a Microsoft product, but I believe it's the one, or at least was one of the first Microsoft product which is open source, so you can download it. It will only run on .NET, of course. And then, although the project state is a bit uncertain right now, there's something called Jython, which is an implementation of Python for the Java virtual machine. Unfortunately, the 2.2 release has been in alpha then beta for like 4 or 5 years now. The main architect of that project has moved to be a Microsoft employee and has been the driving force behind IronPython. So I don't know what to predict for Jython at this point in time. But beyond the technical aspects of Python as a language and of its libraries, Python is also, and this is very important, a vibrant open source community. You will find in just about any field of programming, some more represented, others less, a lot of companies and individuals using Python. The Python Software Foundation is the nonprofit organization which holds all the intellectual property rights to Python. And it's organized in a series of sub-communities that pursue special interests. There's a special interest group on databases, one on matrix computation, one on image processing, and so on and so forth. There are a lot of local interest group. Wherever you live, there's likely to be an active Python interest group meeting once a month or so. I'd like to put in a plug for Bay Piggies, which is a local interest group for the Bay Area, San Francisco Bay Area, which meets at Google every month on Thursday, and the next meeting is 2 days from now, so you're all welcome to show up. It's a beginner's night, meet and greet night, so there's no specific theme this time, but it's certain to be an interesting experience. And there's an enormous wealth of websites, news groups, and mailing lists for all sort of general and specialized discussions. There's plenty of courses, workshops, tutorials. Just in the Bay Area over the last year, I've seen something like 4 or 5 different courses offered by various local universities, plus other offered privately. And there's an inexhaustible array of books. That includes online-only books, a few of them, paper-only books, a few of them, and most of them, of course, available in both ways. So I will spend the rest of the talk explaining the good and bad points of each of these books. Nah, not really. But I wanted to threaten you. Of course, I think the best one is this, the Python Cookbook. It's the best one because I wrote it with my wife. But the second best is Python in a Nutshell, which I wrote on my own. No, seriously, they're not, well, Python in a Nutshell is not really a book for beginners. It's a reference book. Python Cookbook is reasonably suitable for beginners because it shows you how to do hundreds of tasks. For beginners, there's a lot of other great choices. For example, Python for Dummies, written by two other Bay Piggies members. And another one I know very well is Core Python, written by yet another Bay Piggy member. And of course, some are about Python in general, some are much more specialized. For example, Python network programming is about using Python specifically to program network. TurboGears is a specific Python framework for websites. Jython is an implementation I already mentioned. Data crunching is essentially about using Python and other tools to take data files and do useful stuff with them. So chose wisely. So I claim this talk is addressed to people who already know to program in various other languages. And therefore, I'd like at this point to introduce how does Python resemble some of them in different ways. The most important similarity to Java is in the typical implementation. Python, like Java, is normally compiled to bytecode. It doesn't need to be. You can make machine code. With Python, you would do that using PyPy 1.0, which has a lot of backends, including, I believe, Intel-only machine code. But it doesn't really buy you much, as people who've tried to compile Java with the GCC Java compiler know. Compared to a well-tuned virtual machine, it doesn't really buy you much. One crucial difference in operation between Python and Java is that in Python, compilation is implicit. You don't normally bother to explicitly compile your files. You just leave the sources laying around, and whenever you import one, the Python runtime system finds it's not being compiled yet. It compiles it on the fly. It's a very fast compiler. You hardly notice the fact, and then it saves the object file to disk, so next time it won't have to. Everything inherits from object, except it's lowercase o versus the uppercase, but the difference is that we do mean everything. Numbers inherit from object. Functions are objects. Classes are objects. Everything is first class. There's no need to make strange things. Just take a function object, just take an integer object, and stick it anywhere else where you would stick any instance you wish. Like Java, Python has uniform object reference semantics. Anytime you assign A to B, you're not copying all the bits of A into a box called B. Rather, you're attaching a label called B to wherever label A was already attached. So same goes for argument passing, same goes for return. The difference, again, is that this does apply universally in Python. We don't have special cases whereby this is almost always true, except for numbers. It's got a vast and powerful standard library. Java's is like twice as big, I think. But after Java is maybe the largest standard library of any language in wide use today. It's got garbage collection. Again, there's a little difference in implementation. If you look at implementations such as Iron Python, it will, of course, piggyback on whatever garbage collection semantics are offered by the underlying platform. Or Jython will use exactly the garbage collection semantics of the JVM. Classic Python tends to have a dual system of garbage collection to collect garbage as soon as possible. It uses both reference count and mark and sweep, if you're familiar with the issue. But that's an implementation detail. And then it's got all sort of cool stuff, at least for people coming from C and C++ and not used to having them, such as introspection, which I believe Java calls reflection instead, serialization, threads as part of the library, and so on. In other respects, Python is rather more similar to C++. For example, number one, it's multi-paradigm. In Java, you want to write hello world, you have to write a class, even though there is no conceptual need for any class, you still have to write one because Java forces you to. In Python, like in C++ or C for that matter, if you want to write just a function, you write just a function. Don't need to force a class around it. Besides, like you can do object-oriented or procedural, you can also do generic programming. Essentially, in C++, you have to do that explicitly through templates. In Python, essentially, it comes for free, as we'll point out later. And a little functional programming, because you can pass functions around, which is notoriously a problem in Java. It's much easier in Python because you don't have to think in terms of pointers to function. You can actually think in terms of passing a function, returning a function from another function, just like you do in functional programming languages. There's multiple inheritance. It can be used in structural ways, but that's a very controversial theme in any language supporting multiple inheritance. Or it can be used in a very nice way, which is a mix-in. If you go to the web on the Google video site, you'll find my talk on design patterns for Python. Second part, I show how to use mix-in inheritance for a very powerful class-level implementation of what's essentially the template method design pattern extended to a whole class. Okay, signature-based polymorphism is basically the same thing as generic programming at some level, except, again, that in Python, everything is a template. So the features needed from a certain argument to a certain function are defined, but what the function actually does with it, what methods it calls on it, what operations it does on it. In C++, you explicitly say which type parameters are in play. Also, what C++ and Python have in common is that for just about anything that isn't a core issue of the language itself, things which we could call side issues, except that they're typically at the core of any serious programming you may ever do, you've got even too many choices. What you want to use as a graphical user interface, in Python you can basically use anything you can use from C++, plus anything you can use from .NET if you're using Iron Python, anything you can use from Java if you're using Jython, plus more. So you have even too many choices for a graphical user interface framework. Similarly for how do I go on the web, how do I do other network operations, how do I interface to databases, how do I do communication between processes, distributed computing, and so on and so forth. For all of these things, some languages offer you very strong guidance. Python, like C++, basically tells you to do your own choices. One of the most interesting similarities to me is that even though a sufficiently superficial observer would claim that C++ or Java are very similar to C, and Python is different because basically it's got no braces, or it doesn't use braces for structure the way these other languages do. If you look at what defines C, the situation is actually very different. Fortunately, the ISO standard for the C language in its rationale offers a 5-point definition of what is C all about, what is the spirit of C. 1, trust the programmer. 2, don't prevent the programmer from doing what needs to be done. 3, keep the language small and simple. 4, provide only one way to do an operation. And 5, make it fast. Okay, On point 5, unfortunately, Python isn't all that adherent to the spirit of C. But on 4 out of 5 of the points, Python's principles are exactly the same as C's principle. We don't put a lot of infrastructure in place because we don't trust the programmer, like Java does, like C++ do. All those private, public, semi-private, semi-public. If you trust the programmer, that's useless baggage, so we don't have them. And therefore, we keep the language small and simple. And we never stop the programmer from doing what needs to be done, because anytime you try to make something, well, first of all, you cannot make something foolproof because fools are so ingenious. That's a well-known fact. But anytime you put in place something to constrain the programmer because you don't trust the programmer, you are, in certain sufficiently nasty situations, stopping the programmer who you should have trusted from doing something that needs to be done. So point 1, 2, 3 go very well together. And point 4, the first time I read that design principle for Python, it's very contentious in today's world. The way the principle reads in Python is there should be one and preferably only one obvious way to do it for any do it. Anytime you do have a way to do task X, having another one is sheer waste. You're just making the language bigger. Don't. Of course, it's a target, it's a dream. Even in C, there's often more than one way to do an operation. You can, I don't know, have a pointer walk through an array or use an index to walk through the array. They trust you to do the right thing. But these are never desired the way they are in some other languages. For example, there's one language which is generally very similar to Python, but with very different philosophy, which decides that since programmer never can remember if an array has a dot size or a dot length, well, they would offer both with exactly the same semantics. That is exactly the reverse of Python's philosophy. Having several ways to do something fights against uniformity. I told you uniformity is a Python value. If we all manage to only have one way to do it, then everybody would be doing it the same way, which means maintenance and teamwork would be vastly enhanced. This part isn't exactly met, unfortunately. There are some choices which may not be all that important today, but for example, Python does not define the semantics of floating point numbers. Exactly like C or C++, it says the semantic of floating point number is whatever this hardware says it is. Nowadays, this isn't very important because basically all reasonable pieces of hardware have similar semantics. But it used to be a big deal because, for example, all the Cray supercomputer had their own semantics for floating point. A language such as Java, which says this is exactly what the semantics of floating point numbers is going to be, could never have run on a Cray supercomputer at a speed faster than a snail. For Python or C, we'd rather give up some portability, so the floating point computations are not guaranteed to work the same way on an old IBM mainframe, Cray supercomputer versus VMS, VAX VMS machine. So in this sense, we have made exactly the same design choices as C. Truth be told, it's partly laziness, because this way we don't have to provide a complete software implementation of floating point on those machines whose semantics are not entirely precise. So far I've tried to stress some similarities and only minor differences, but of course, we can also go the same way and see how is Python different from all of Java, C++, and C. Here the big deal is that typing is strong but dynamic. Strong, much stronger than in C, for example. In C, you can basically use a cast to say, these bits, whatever they may be, make believe they're a float, which basically destroys your type system. You cannot do that in Python. On the other hand, the typing is dynamic. Another way to put it, a name has no type. A name is a name is a name. The type belongs to the object, and the name may refer to an object, but then it may change and refer to a different object, so the type may change. There are no declarations, just statements. Basically, there's no distinction, no conceptual distinction between compile time and runtime. Compile time where the declarations are something that guides the compiler, and runtime where the statements are actually executed. We don't draw that distinction. Things are just executed as you go, conceptually speaking, even though, of course, there is a compilation stage for speed. Syntax is very spare. Ornamentation is absolutely minimal. No braces for blocks, just indentation. No parentheses around the conditions in if and while statements. Less punctuation in general. Interesting observation I've heard on this point is that Python is the only programming language designed according to the principle of Edward Tufte. If you've read the visualization of quantitative information, you know that his core principle is no wasted pixel. One pixel that is there just because it looks nice is a waste. Take it out. Python doesn't have any extra pixels. Well, we do. We have some full colons which could be removed, but they're very tiny pixels. So everything is a first-class object. By everything, I mean classes, functions, methods, modules, packages, just about anything you can think of. It doesn't exist just at compile time for the benefit of the compiler. If it exists at all, it's a full-fledged object. It exists at runtime. You can put it in a list. You can return it from a function. You can pass it as an argument. Also, while Python lets you twiddle bits, it's not really what it's meant to do. The focus, where it really shows its strength, is on the high and very high levels of abstraction. So, fundamentals. There's an interactive interpreter. It's not the main normal way to use Python, but it's nice to try things out and explore things. The prompt is 3 greater than signs, so the secondary prompt, like in Bash, here it's ... It means statement continuation. Normally, you write source file, foo.py. First time you import them, we'll see what import means in the language in a while. It gets compiled to PYC, the object code, and therefore, after that, it's simply loaded from there. The simplest instruction in the world is a plain assignment, which just says name equals expression. It binds or rebinds name. This is not like it would be in C or C++, an operation between objects. It's an operation between an object, whatever the expression means, and a pure name. A variable is just a name. That's like it would be in Java. This has absolutely no effect on whatever name used to indicate previously. It just means that from now on, name indicates this one. There is no declaration of name. Whenever you bind something to a name, the name springs into existence, and names don't have a types object, as I already said. There's a special object called none, which is a placeholder value, meaning there's nothing here. That would be roughly the equivalent of null, lowercase null in Java, uppercase null in C, where meaning there's nothing except I'm still holding the place for something to come in the future. For example, a function that doesn't have an explicit return statement will return none. However, none is a full-fledged object. Again, you can pass it as an argument, return it from a function, put it in a list, and so on. Everything is first class, including nothingness, very Zen concept. The elementary I/O, which you never use in real programs, but is nice in some, to like write short examples, didactic example. There's 2 simple built-in ways to do input. One is the function called input, which basically lets the user input any expression whatsoever, computes the expression on the fly, and inputs the result to your program. Of course, that's not something you'd ever want to do in a real program, because if there's a syntax error in what the user is typing, you're going to crash. And row input, which is the same thing, but just returns the string that the user has typed, just trims the trailing new line And for elementary output, there's a statement called print, followed by 0 or more comma-separated expression, which just puts them out on standard output, one after the other, and a new line at the end, unless you have a trailing comma. There's no fancy formatting there. If you want to do fancy formatting, you can have your comma-separated expression be a string formatting expression, as we'll see. But print itself, it just copies stuff with this absolutely minimal formatting the space in the new line. Of course, again, it's not meant for professional level output. There's a bazillion other ways to do that. Okay, so here's some trivial example of what we've seen so far. Whatever name X meant before, including nothing, it now means the number 23. So if you print X, then 23 is what you get on standard output. And then X is now the string foo. So nothing bad happens to 23. It's not damaged in any way, just not referred to by name X anymore. Now print X, image foo. So see, the name X per se doesn't have a type. At this point, the object shown by X is an integer, and at this point it's a string. But also one thing you can do in Python, which is typically not available in other languages, is to delete a name. That doesn't damage the object in any way, again. It just takes the name out of the issue. So the name X doesn't refer to anything. And if you do a print X, you get an error at that point. On the other hand, if you want the name Y to be around, be usable, but not mean anything special, you can assign none to it. That's a placeholder. And now you can, if you want, print it, and you will see the letter N-O-N-E. No big deal. Python has flow control. There are three. We'll see how one of them is defined in terms of the others, but that's a bit later. If, while, and for. If is the only way we do conditional operations. You may have else if, which is spelled elif. You may have an else, meaning in every other case. There's while. While accepts inside its loop body break and continue, same semantic as in all of the three languages. And it can also have an else. This is not common to the other languages. Essentially, an else in a loop in Python means if the loop has terminated normally, has not been prematurely interrupted. Essentially, a break terminates a loop prematurely. The else is what happens if no break has executed during the loop. And then there's for, which is basically having a name step through a sequence, an iterable as we call it. It can have break, continue, and else, just like while can. Here's some simple flow control example after a couple of preliminary assignment. Let's see which one of these statements, these print statements, would you expect to be printed? Who thinks it will say A is greater than B? Nobody? Who think it will say A is equal to B? Who think it will say A is smaller than B? Well, somebody. Most of you don't believe it will do any of these things. It will do one, and yes, it's of course the last one, just to show how easy it is to understand the semantics here. And let's see. If after that we have this loop, what will happen? Well, is A less than B? Yes. 23 is less than 45, so we print 2345, and this makes A refers to twice.
And if the while had an else?
If the while had an else, it would execute because there is no break. The while terminates naturally because A becomes 46. 46 is not less than 45, so that's it. That's a natural exit. There's no break. It makes no sense to have an else if you have no break in the body because it will never execute. Okay, there's some simple types, or scalars, so to speak, which are a lot of numbers. There's integers, long, floating, complex. I don't know why. I'm an old Fortran programmer. I don't know why other languages after Fortran drop the complex numbers. They're so handy for all sort of computation. Here's some example of numbers. So 23 is a number, and so is this. You may notice that this number is kind of long, but is far from too long for Python. You just keep typing digits. until you manage to exhaust your available memory, which will take you a long time with a typical machine of today with a few gigabytes, Python is quite happy to store your integer. It has multi-precision implicit. You can use like hexadecimal. 2.3 is, of course, a float, which would be called a double in C. And 4.5 plus 6.7J is a complex. We've used J like in electric engineering rather than I, like mathematicians usually do. But it's one of the two recognized notation. There's all sort of operators. Again, Fortran lovers will note we do have the double star, meaning raised to power. Again, I don't understand why it's not a widespread use. There's two forms of division. One means with truncation, the other without truncations. And there's modulus, shift, bit operations, and so on. And there's a few built-ins. We'll come back to built-ins later, but pretty obvious, like absolute value, minimum of number. Okay, it's not entirely obvious to most people. Why should we have pow as a built-in if we already have star star? The reason is that the built-in pow has potentially 3 arguments. It does x to the y modulo z. And if you're really into number theory, you know that can be extremely faster. But that's really the only concession to strange things we have in the built-ins. Okay, and then, sum takes any array of numbers and sums them up. And strings, we have 2 kinds, unfortunately. Here's an example where backward compatibility fights against simplicity. We'll remedy that in Python 3.0. It's obviously simpler, like in Java, to have only Unicode, and it's obviously the right way to do it. Unfortunately, for backward compatibility, we still have plain strings, meaning strings made of bytes, and Unicode strings as well. So we have to explicitly indicate with U colon something, quote something quote, that this is a Unicode string. Otherwise, all the others are byte strings in the current version. And then there's all sort of escape sequences. And you can do catenation, you can do repetition of strings, and you can do formatting, which uses a very rich format language, very similar to the printf function of C. A few built-in, such as CHR, which go, or any uni-CHR, depending on what type you want, go from a number, an integer number, to the corresponding character, and ORD goes from a character to its ASCII or Unicode code number. Strings are read-only sequences. We'll see what a sequence means shortly, meaning you can take their length, you can index and slice them, you can loop over them. And strings have so many methods, it would take several slides just to list their names. But stuff like capitalize the string, center the string in a field of arbitrary length, all sort of cool string manipulation stuff. So we have the built-in simple types, scalars, if you will, and then we have containers. Only a few containers are built in. Most of the container types are in the library. But these are the ones which we have deemed so important that it's worth having them as built-in. A tuple is an elementary immutable sequence. It doesn't do just about anything except it holds immutably a small sequence, typically small, sequence of objects of any type. It's notated with parentheses and commas, and or you can build one by explicitly using the word tuple with a sequence argument. Basically, it's essentially a mathematical concept, but its typical use is very similar to a struct in C, except instead of having the fields be named, they're just numbered. A list is a mutable sequence. Don't let the name list fool you. It's not a linked list. It's implemented as a vector. It's in contiguous memory. So that tells you, if you're an experienced programmer, all you need to know about its performance characteristic. It's notated with square brackets. Again, you can build one explicitly by calling the type with a sequence argument. Set and frozen set are the mutable and immutable versions of sets, which are basically implemented with hash tables. Dict is a key-value mapping, also implemented with a hash table. Again, this indicates the notation. You can always call the type. In the case of dictionary, you don't call it with a sequence, but with keyword. All containers have a length, being the number of items they contain. All containers have looping. You can loop over all their items. And all containers allow membership testing if something is in the container. Most of the containers, tuple is the exception, also have methods that let you do all sort of cool stuff. Set also has operators because that's the most natural way to express operations on set. For example, intersection, you can spell ampersand. Union, you can spell vertical bar. Sequences are a subset of containers, specifically strings, tuples, and lists, plus a lot of other stuff in the standard library, which have some extra things you can do compared with what you can do with other containers. First of all, you can ask for their repetition and concatenation. So given any two sequences A and B of the same type, A plus B is the sequence which has all items of B in order, A in order, followed by all items of B in order. It's a very natural concept. You can concatenate lists, you can concatenate strings, you can concatenate tuples. Repetition is basically the same thing. You could write A plus A plus A, but you can write A times 3 or 3 times A. It means exactly the same, just like it would for numbers. Then you have indexing. Just write the index always starts from 0 in square brackets. You have slicing. You write the two indices with a colon, and you can have slicing with a step where you write start, stop, step. For example, given the sequence ciao, C-I-A-O, ciao 2 is A because we always start from 0. Ciao 3 to 1 by -1, meaning -1, so we're going backwards. So we start at 3, that's 0, 1, 2, 3, it's an O. And we go down to 1, which would be the I excluded. So we do O and A in reverse order, OA. Always first bound included, last bound excluded. If you've read Andreas Koenig's masterpiece, C-Traps and Pitfalls, there's a whole chapter on why all of your loops should be first index included, last index excluded. Read that book, even if you never program in C, it's a great book. Like you should read KNR just because it's a great book, so is Koenig's. And basically in Python, you get that concept built into the language, and it's built in. So lists are mutable sequence. So given an indexing or a slide, you can assign to it. Moreover, if you assign to a slide, you don't have to assign a list of the same length as the slide you're assigning. You can assign a shorter list, will collapse the list. You can assign a longer one, it will automatically expand. That, of course, does mean that these kind of assignments can be very costly because, as I said, the thing is contiguous in memory, so it has to move everything around to make space. Dictionaries and sets are not sequences, so it makes no sense, for example, to multiply a set by 3. It doesn't make any sense at all, so Python doesn't let you do it. Okay, there's several comparisons. If you're familiar with the comparisons in Java, you know why equal is different from what in Python we spell is. It's about being the same object versus being same or distinct objects with the same contents. Containment is also a test spelled in with operators in or not in. Comparisons can chain. So for example, 3 less equal x less than 9 reads in exactly the natural way. Every time you teach any other language to total beginners, you have to explain that this doesn't work the way everybody thinks it would, because it first computes 3 less than x, which is maybe 1, and then it computes 1 less than 9, which is true at least in C, where comparisons are 0 and 1. In Python, it works exactly as everybody thinks it should work, meaning x is greater than or equal to 3 and less than 9. What is false in Python for purposes of if and while and other tests? All numbers that equal 0 are false. empty strings are false, none is false, every empty container is false, and false is false. False with the uppercase F is the Boolean constant equivalent to 0. So if you need something that is false and doesn't need to have any other characteristic, you can have that. Everything else is true. So you see, Python is a very belief-oriented language because almost everything is true. But if you need something that's only true and has absolutely no other interesting characteristic, you can use true spelled with an uppercase T. Not is an operator which always gives you a Boolean, so not x is always the same as not bool x. So not of an empty sequence is true with an uppercase T. Not of a non-empty sequence is false. I keep seeing people who come to Python from other languages check if a sequence is empty by asking if len of that sequence equals 0, and that is wrong. It's simply if not that sequence. For example, say members is the set of members of your association. To do something like close the association if it has no member, if not members, close association. That reads pretty natural. Not if len of members equals 0. And an OR operator short circuit, like ampersand, ampersand, and vertical bar, but very usefully, they always return one of their operands. So not necessarily true or false, but any operand you've passed to them. By short circuit, it means they don't bother to evaluate the right-hand operand if by the left hand they already know. For example, false and anything is false. True or anything is true. The right-hand operator might potentially even cause any kind of side effect. That side effect won't happen. That's guaranteed by the language. There's also built-in functions any and all, which can be called with any number of arguments, which do essentially the same thing, but on sequences of arbitrary length. Basically, they terminate as soon as the result is known. Unfortunately, there is no way to do that on empty sequences and still ensure that something is returned that is in the sequence, because nothing is in an empty sequence. So therefore, any and all don't have this handy feature of always returning an operand. They return a bool. Still, it's potentially useful. Like in C++ or Java, errors are handled through a concept known as exceptions. Not only errors, but also anomalies that aren't errors. Python uses a lot more exceptions than would be considered good style in either C++ or Java. Exceptions are instances of built-in type exception or any subtype of it. There's a statement raise if you want to make noise explicitly. They propagate along the stack of function calls, terminating the function as they go until they're finally caught, or if they're never caught, your program is history. And typically with a trace of the error that wasn't caught. You can use statement try except to catch exceptions. You can use try finally to not catch exception, let it propagate but guarantees that some termination operation is done. You can use the nicer form with, which lets you implement the resource allocation is initialization idiom. Now, I mentioned a for statement as being separate for a while, but the interesting thing is that the semantics of for are defined in terms of those of while and a concept known as iterators. So basically, for I in C something means make a temporary variable which is the iter of C. Iter is a built-in function that returns the iterator for any container. And start looping. Try getting the next item from the T, then it's I. If there's a stop iteration exception, that's it. And then do the body. They're not exactly the same because an else clause in this for might execute while an else clause here would not execute because the only exit is via break. But this is the essence of the equivalence. And you can also build, you can also have for embedded in an expression in either parentheses to just make an iteration or square brackets to make a list. This is known as a list comprehension, and this is known as a generator expression, or for short, genexp. The optional clauses mean you can nest further for and if clauses to nest looping or selecting whatever you're doing with. So the main way to organize your code is function. It's highly recommended to have all of your executable code in function. Among other things, since a function is a well-delimited unit, particularly if you write small functions, Python can optimize much better. Try making exactly the same code at the global level in a module versus inside functions in the module, and you'll see what I mean. You can go 2 or 3 times faster if you have everything properly organized in functions. So there's a name, def, which is not the function, name, parameters in parentheses, and a body. The point is that when def executes, and remember def is an executable statement, there are no declaration. When the statement def executes, the body doesn't execute. It gets compiled, but then the compiled form is saved as part of the function object that's generated. And that function object is assigned to name. The parameters are 0 or more local variables which get initialized by the caller. So like in C and its derivative languages, parameters are the same things as local variables, except their initialization happens at call time. You can have default values, like in C++, only to training parameters, again, like in C++, by writing equal some expression to the name. However, the expression is evaluated only once. The expression that makes up the default value is evaluated when the def statement executes. And so therefore, anytime you make use of a default value for a parameter, it's going to be exactly the same object. Parameters may end with star name to take a tuple of arbitrary positional argument, or star name to take a dictionary of arbitrary named argument, which is basically useful when you want to make functions, what in the C are called variadic functions, which take an arbitrary number of parameters. Here's an example of function. First of all, the most simple, obvious way to do a sum of squares. Take A and B, they're the parameters, and do A times A plus B times B. By the way, as any old-time Fortran programmer will tell you, the fact that you have the raised to power operator doesn't mean you should use it to do squares. A times A is actually faster than A star do 2. It's probably not true in Fortran anymore because the Fortran compilers have become pretty smart, but Python compiler never tries to be too smart. It says, gotta be a reason this guy has written A star 2. I'm going to compile exactly the bytecode to compute the power. And that's slower than the one that computes the multiplication. So remember, do it as if you didn't have the raised to power. So you can just print the sum of squares and you get the area of the square built on the hypotenuse. But why limit yourself to 2 sides? I mean, Pythagoras would be happy because this is what you're doing, but you don't have to because you can take an arbitrary number of parameters, and this is how you sum them all. Sum all of those square. Remember our syntax for the generator expression. Expression for some item in a container. Here's exactly what we have. Expression, x times x, for x, arbitrary name for an item, in the container. A, the tuple of all arguments passed to the function. So this works just as well if you print assume SQ2345, but you can keep passing arguments and it will work just as fine. This is the low-level equivalent. It's okay, I mean, it works. But Python tends to have a, there's a concept, a very important concept in C++ known as the abstraction penalty, something Dr. Stepanov has been measuring for decades now. Basically, how much does it cost me to do things right and work at a high level of abstraction rather than very lower level closer to the machine? And slowly, gradually, as C++ compiler become more and more complicated and sophisticated, it's slowly going down. Python does things differently. We typically have an abstraction reward. The more abstractly you program, the further from the machine and the closer to mathematics and to your problem, the faster your code will go. Try it. It's very easy. Get a Python interpreter, check how long will this take for a dozen arguments versus how long will this elementary, lower level, closer to the machine expression take. Since we're on the subject of loops and functions, I should mention generators. Generators are functions which, instead of return to give a value, and return gives the value and terminates the function at the same time. That's true in any of these languages. They use yield. Yield gives a value but suspends the function ready for the next time. And by the next time, we mean that when the function is called, it returns an object which has a method called next. Every time you call next, the function restarts from wherever it last yielded. The first time it starts from the start, and then every time it starts from the last yield where it got suspended. This is particularly suitable for looping in a for because of what I mentioned before on iterator. Having the next method means you can use it in a loop. Just to complete that, when the function ends, it has yielded all it, and it runs off the end or hits a return statement, then it raises a stop iterator. So if you're using it in a for, it exits normally. For example, this is actually built-in, but if it weren't, this is how you would make something which, given a sequence, gives back one after all of the items of the sequence, each with its proper index, 0, 1, 2, 3. So you pass it quote, chow, quote, it yields first time 0C, then 1I, then 2A, then 3O, and then raises stop iteration. It's not very difficult. You start with n equals 0, loop over the sequence, and yield n and the item. At this point, the function suspends when it's yielded the first pair. Still ready. All of its local variables, n in particular, are still perfectly intact. When you call next, or at the next iteration, n gets incremented, and you do the next stop. So you're suspending in the middle of a loop, ready for the next time. Very handy. This is an example of how handy it can be. A generator, I said the function will raise stop, the object returned by the function will raise a stop iteration when there's nothing more to yield. But I should have said if and when, because this is a case in which it just keeps going. Well, it will eventually fill up your memory, since at some point you will have integers that take about a gigabyte each to represent, and you will be running out of memory. But it will take quite a while. So this is a Fibonacci sequence from my compatriot, well known as one of the first arithmeticians. It starts with ij to 1, and while true, oh, this is, by the way, something I didn't really mention, is a multiple assignment. I'm simultaneously assigning to r, I, and j the expressions I, j, and I plus j. So the whole, everything on the right-hand side is computed first, and then everything on the left-hand side is assigned. So you don't have to worry about I and j changing on you when you're still using them here. It's a simple multiple, it's just a multiple assignment if you've ever used SML or Haskell. R is whatever used to be in A, the number of rabbits actually, and so we yield it. And we never end. The problem that Fibonacci was discussing in his book is I have this farm raising rabbits, and I start with only one rabbit. After when he's 2 years old, I get as many rabbits as I had in the previous 2 years. So this is how the sequence So this is how we use it. We have to explicitly break out of the loop at some point. In this case, I'm going to sell the farm when I have more than 100 rabbits and retire to some less stressful job. And this tells you how many rabbits you'll have to house every year. Closures, well known to every functional programmer, but just I did mention very briefly that closures are unnatural in Python. Actually, I said, like in C++, they're actually much handier here than in C++, because we exploit the fact that def is an executable statement that creates a new function object, and we also exploit lexical scoping. You can't have nested function in C, so it's not really. So this is the trivial example. We want to make an adder with a given addend. Well, we simply make a function which takes the other summand, which is known as the outgend. Nobody knows that, though, but I do, and returns the outgend plus the addend. And from the make adder, we return header. So make adder variable here is looked up here. So we can print A23 of 100, A42 of 100, or one of the other, and everything works. There's no interference. They're kind of like, it's kind of like instantiating a class, except that it only applies to a very narrow set of use cases, but it's very useful to have because it's so much simpler. Decorators are purely syntactical form to apply higher order functions, basically to wrap a function into another function or function of function and assign it. It's kind of handy. Okay, there's two styles of classes in Python for backwards compatibility reason. I'm only going to talk about the new style classes. Forget the existence of legacy classes. You have to give some bases all the time. There are other methods, but if you don't have any bases you care about, just write open paren object, close paren. Everything inherits from objects, so you're not going to break anything. So it's class, name, basis, and a body. And the body is just a series of statements of your choice, but they're invariably def and assignment statements. Everything that you're defining or assigning in the body becomes an attribute of the class object. And also, all the attributes of the basis are attributes of the new class object, unless the new class object overrides them with something else with the same name. So to create an instance, you just call the class. That's very handy because basically, you can easily make a function that takes as one of its argument something which gives it something else, just calling it. It doesn't have to know whether it's a class object or a function object, it just calls it. So this is an example, which is why I'm calling it EG, for example, given. We have a class attribute, a simple list, empty initially, and this is an attribute of the class, so shared, if you will, by every instance of the class. This, on the other hand, we assign as an attribute of self, which is the way we refer to the object, the instance. And this is an empty dictionary as a variable of the instance. We have a method which appends something to the class, CLA, the class variable, and we have another method which assigns some item to the dictionary. And we make two of these instances. Then, okay, in the beginning everything is empty. Then we call the methods a few times, and now we see that the class attribute is actually being modified twice, by 1 and then by 4, while the instance attributes are separate. So we can check with the is, are they the same object? Well, in terms of the class attribute, yes, because these are two instances of the same class. In terms of the instance attributes, no, because they're instance attributes. Whenever you look up a method on an instance in order to call it, or for whatever other purposes, the lookup and the call are totally separate operations. We go to the type of the instance, which would be class if you'd rather, call the method, and implicitly pass the instance as the first argument, the one we have called self previously. Whenever we do the lookup, this is what happens, except for descriptors, which I'm not going into here, a very important mechanism. First of all, we look in the dictionary which belongs to an instance. Every instance has a dictionary, and we just can look up the name. If that doesn't work, well, we are going to look in the dictionary of the type of the instance, the class. If not there, we do the same thing for each of the bases. If not, we try this special method called getUtter in case somebody has defined it, which can essentially build dynamically just in time whatever is meant to correspond to that thing. And if everything fails, we raise an exception, an attribute error. These are example of subclassing. Remember that class EG? Well, we're overriding method. We're overriding it simply to give y a default value. Then we just call our superclass, or we can also use a word super to do that. But I honestly find this more readable. This is pretty obvious. I'm calling the method on Mr. EG and passing it. So this isn't so obvious. Another example, we can override data. Suppose we have a subclass of list, which each time you append something, appends it twice, a repeater. Well, then we can subclass sub and override the class variable so that all the methods are the same, but the class variable is a separate one. Another important concept are properties. Well, I said I wouldn't talk about descriptors, but these are, of all the descriptor types, these are the most important built-in descriptor type, the property. Say you have a getter method, which without any argument returns a value, and a setter method, which given a value does something with it, presumably assigns it somewhere, somehow stores it in the class. Then you can wrap the getter and the setter in a property and assign it to a name. Now, if you have an instance of this class, every time you access the name, you actually call the getter. And every time you assign to the name, you actually call the setter instead. So this is basically a property that basically offers you syntax sugar so that instead of calling an appropriate method, you can just act as if you were accessing an attribute or setting an attribute. Why this matters is that this way you never need to hide attributes behind the getters and setters. Anytime your class has an interesting attribute, you just expose it. Forget encapsulation. It was invented before the concept of property was invented. The point is, if the next series of your code suddenly doesn't have that attribute anymore and needs to compute it, rather, just write your getter method and wrap it in a property by that name. You're done, no problem. All of the code keeps working. All of the code that using the class doesn't need to do anything special, it just works. Avoid boilerplate. If in Python you ever see somebody writing def get foo, self, return self foo, you know this guy hasn't learned Python yet. Python, like C++, affords operator overloading. There's legions and legions of methods. We have 2 underscore right at the beginning and end of the name because basically these aren't meant to be called directly. The Python will call the special methods on the type as appropriate. Don't call them yourself, with rare exception. So that's why we made them ugly, so they wouldn't be tempted to call them. For example, these methods let you define the semantics of comparisons. These let you define the semantics of arithmetic operation. These define semantics, basically defining how is your type a container, how you get item, set item, delete item, how you know how long is an instance, and so on. For example, this is the equivalent written out in full as a class of that handy Fibonacci generator I showed before. This doesn't use the suspended function concept and so on. It just does things ploddingly. It uses the init method to do initialization. The ij, which I used to have, are now explicitly indicated as instance variables. It uses the iteration special method returning itself because it is an iterator. And it has the next. This is meant possibly for calling yourself, so it doesn't have the underscores. But it's still a special method. And it does basically the same computation as we did. Of course, and of course, it's using exactly the same way. You see why we'd rather write a generator which was like 3 lines instead of 7. But the point is that internally, the generator essentially builds something like that. So don't call special method directly. Built-in functions and other operations do it right for you. For example, definite example, somebody doesn't know Python if he gets the absolute value by explicitly calling under, abs, under. What he should do is called abs. Abs will do whatever is proper. Because that may include, okay, try this special method. If that special method is not there, try comparing with 0, possibly change the sign, all sort of stuff that happens under the cover, and you don't normally want to bypass it. There's plenty of interesting built-ins. And most of the other interesting stuff is in the standard library. Okay, here's an example using 3 built-ins. I have highlighted them. We want to build an index for a text file, meaning we want to print in alphabetical order all the words in the text file, for each word, the list of line numbers where that word occurs. So, first of all, we build a dictionary, which maps a word to a list of line numbers. We start with an empty dictionary. We use the with statement because that guarantees, it's like a try finally, except it's nicer syntax. It will open the file name, give us the result as file F, and then intrinsically close F when we exit by any means whatsoever. Then we use enumerate, which gives you line number and text of the line. Split the line, that's one of the many methods of strings which I mentioned, which splits into words. Set default is a method of the dictionaries, which basically assigns something if it wasn't already, assigns a value if there wasn't already anything assigned for that value. Here, our default is the empty string for that given word, so the empty list, I'm sorry, so we can just append the line numbers. So we're building up our list of line numbers. Okay, when we're done with these 5 lines, we have our dictionary, and now we only need to display it. So we wanted sorted versions. The natural comparison of words is alphabetical. Well, may not be, like all lowercase comes before, all uppercase come before lowercase. It's a typical ASCII order, but it's good enough for me. And we just use print with a little bit of formatting and a comma to not break the line yet. We loop over all the line numbers for the index of the world and print them again with a comma to not break. And finally, we do an empty print just to break the line. So there it is. This is a complete index and display of the index of a text file. I once tried coding it for C++, in C++ just for fun, but I gave up because it was just a joke. The code is totally unreadable on a slide. And the funny thing is that this is actually typically faster in Python.
So if on one line we have one word multiple times?
This is printed multiple times, yes. We are carefully doing that, yes. Yeah. The alternative, of course, would be to essentially map a word instead of a list of lines, map it to a set of lines. So sets intrinsically have no duplication. So if you only want one occurrence, well, instead of these square bracket, use a set, open, close paren. And instead of append, call add, which is how you add items. And here you would have to use sorted if you want the line number to be sorted. So you would have to change 2 teeny spots here and 1 teeny spot there, and you would avoid duplications, if that's what you want. Okay, so I did say Python points a lot on modularity. So how do you import the modules? The library is full of them. You just import module name, or from some.package import module name. And then you just use module name dot whatever you want. There are shortcuts available, but they're never recommended. You don't just inject an alien namespace into your own. It's not a good idea. Namespaces are good. Use them. You may short a name using as. This, understandably, if your file is called long module name and you need to use it a lot, you don't really want to type it many times. So import long module name as Z, and then you use Z dot whatever. Or you can import whatever directly from the module name, but then it's not obvious to all the readers of the program where does this whatever comes from. And this is the worst of them, the import star, import everything. You basically inject all of the namespace into yours. That's like, if you're into C++, it's like using namespace. Foo, it's evil. It's a bad idea, don't use it. Okay, this is an example. We use the artan2 function. We import math and then use math.artan2. If we try to use a bare artan2, we get a name error. We could, but we shouldn't, import the function from the module or import everything from the module. Now, math is one example where I can see it doing, because you need to do a lot of mathematics. But avoid the temptation. It's handy in interactive session if you're using Python as a calculator. You can define your own modules. It's trivial. Every Python source file is a module. You just import it. It must reside in the import path. You can also have their bytecode files, which is what Python made for you, or you can have binary extension, which you can write in C or use Pyrex, Swig, and a lot of other tools. So a module is a simple object with attributes, no methods. It may have functions, but they're not methods. There's no implicit self. The attributes are also what you inside the module see as the top level names. They're bound by assignments, class, def, import, and from statements. They're also known as global variables, although not only variable. Not all of them are going to be variable, but still. And you may bind or rebind them from the outside. There's nothing stopping you from doing it, but don't do it. Unless you're doing tests or like mock object and the like. A package is a collection of modules organized in another module. It's mapped to a directory. To distinguish which directory is just directories, which are packages, if they're packages, they need to have an initpy spelled with the use of double underscore, which is the module body. And the modules are all the py files which are in that directory, and the sub-packages are subdirectories which have their own initpy. The parent directory must be in syspath, and you can import foobar or from foo import bar. This is basically all I have to say about the language Python. And then there's a library, which back before Java started spreading, Python is a few years older than Java. Back in 92, 93, the size of Python standard library was scarily bigger than any other standard library ever released. Even with Java 1.0, Python was still larger. With Java today, okay, I give up. Java in a nutshell is 1,600 pages. I was criticized because Python in a nutshell is 700 pages. Oh well, can't beat them. So we have 190 modules at the top level, so to speak, doing anything from math to system operations, random numbers, sockets, RFC 822 or 2282 by now, 2822. We have 13 top-level packages organizing 300 modules, all having to do with a Berkeley database, Python's own built-in compiler, and so on. We have a lot of encodings for all sorts of Unicode operations, a lot of unit tests included in the library, and a lot of stuff that is not normally distributed with binary distributions, which are very nice. You should get from the source distribution demonstrations of how to best use this and that feature, and tools, which are actually very helpful, little scripts and the like. And then, beyond what comes with Python, there's a site, Cheese Shop Python org. Python is named in honor of Monty Python, and the Cheese Shop is named in honor of the Cheese Shop sketch. I checked Sunday, how many modules do we have, packages do we have today, and we had exactly 2,222, which I do it as a good omen, whatever. And these are the main subjects. Of course, software development, everything is about software development. It's not very helpful. There are other, but these are the popular ones. These are possibly a better, more useful way to organize things. There's a lot of way to write graphical user interfaces, SQL databases, and wrappers, object on top of relational databases, all sort of computation stuff, all sort of net and web stuff, development environments and tools, games, games meaning frameworks to write games. Don't know if you've heard about the Pi Week context. It runs a few times a year. You have 1 week to write a video game from scratch. From the moment the thing, everything happens on the internet, so you can have a team, whatever. Everybody uses Pygame and the Python programming languages. Some pretty cool game have come up. People give you the theme, it's revealed at the start of the competition, and then the clock runs for a week. The only problem is you probably want to take a week off, whatever you normally do, study or work, because otherwise other teams are going to do that and they'll destroy you. Other multimedia visualization, scientific visualization mostly, and integration with those sort of languages and platforms. Let's go 1 micron deeper to see what's in the standard library. There are some fundamental things that would be in the language, possibly in many languages, like bisection algorithms, how to copy things, more collections beside the built-in ones, tools that functional programming, an implementation of heap priority queues, tools that is iteration, regular expressions, threading and the queues for it, a lot of tools for testing and debugging, file and text processing, persistence in databases, time and date, but there's one crucial category missing here. None of the standard time and date module deals with daylight saving time. Essentially, the Python core developers punted. We just can't bear to release a new Python release in a hurry because some legislative body has decided that daylight saving time will actually start there and finish there. Remember, there are 165 legislation in the world. We would basically have to do nothing for this huge package that is Python, except following news for 165 countries and states and things in the world to know what are they doing with it. So you absolutely need a third-party helper, either one that uses the stuff that comes with typical Linux distributions or a standalone one. They're both pretty good. Okay, then we have computation stuff and tons of net and web stuff. I've given up on summarizing how many tools we have for net and web. Okay, this is when asked what do you think is the best example of Python, what the creator of Python, Guido van Rossum, currently a Google employee, gives. He says, I never like sitting down at a machine and try wget something, because I get my presentation. It doesn't have wget. Well, it does usually have Python, and it takes me much less time to code up wget, a simple version, than to find it and download it, install it, and run it. And this is how you do wget in Python. Essentially, there's 3 uses of the standard library. So you need to import the module sys urllib, which deals with URLs, and OS, which deals with the operating system. You need to define a hook function. In this case, we just print a file name followed by whatever feedback argument we're given. This is what the urllib retrieve calls every time it gets a bunch of stuff from the net. And so we loop over all the arguments, strip them their URLs, so we strip them to their base name, and we download them to this file name with a little printout, and URL retrieve does the job and calls once in a while, calls the hook. And this, where does what?
The variable fn in function hook.
Oh, it's right here, global. It's remember, def is executable, and the body is not executed at the time. It's only compiled. so there's no need to look up fn. By the time hook gets called, fn has been assigned here. You don't need to declare fn anywhere. Everything is executable. And the order of execution is def executes, but this doesn't need fn. Then the for execute, then this assignment, and then this, which calls back. And this is where the body gets executed. Yeah, I see a lot of people in cases such like this say fn equal none, as if it was a declaration. Don't. There's no such thing as a declaration. This is the exact equivalent. In my multi-threaded version is not quite as similar, but then multi-threaded is never is. It almost is because thanks to the thread-safe first in, first out queue, basically this has just a little bit of extra to declare itself a daemon, so it won't keep the program alive, but then basically the body is essentially identical. It gets the URL from the queue, and then the main program, so to speak, only needs to build a pool of workers and put everything, all the work requests in the queue, and they'll just do their job. I've measured this is actually much faster, particularly in multi-core machines, because the other version basically spends all its time waiting for the internet. So that's a case where multi-threading is definitely worth it. And this is just a few more packages on the standard library. I'm not really able to do it justice, except I'll mention one. Essentially the foreign function library for Python C-types. C-types, you need to know which platform you're using, because basically you can call arbitrary C function from a dynamically load library, but you need to know which dynamic load library you want. So for example, if you're on Windows, you want to load MSVCRT, the common runtime library that comes with Microsoft Visual Studio. If you're on Darwin, which means Mac OS, then you want to load libcdialib, else you're presumably on Linux, or otherwise you need to keep testing, and then you'll want to lead libso. Fortunately, any of these libc objects will have a printf function in C, to which you can pass a string, and will return the number of characters printed, and that had better be 12. So this is just an example of how you can call arbitrary C function from Python. And that concludes my talk. Thank you very much. I think we do have time for a little question and answer.
If your multi-threaded wget runs faster on a multi-processor machine, does that imply that Python can run multi-threaded?
No, it implies the kernel can. Remember that dealing with the TCP IP stack is not exactly zero CPU load. So if I have 2 cores, I haven't actually tried with more than 2. 2 is what I have in my MacBook. Then it means the kernel can be running the internals of socket reception, Nagel algorithms, whatever else, while the application is preparing to request write it as the next thing.
You mentioned that there is an implementation of Python in Python. What's the
Yes.
background behind implementing Python in Python?
Essentially, there's many. To convince the European Union to finance the project to the tune of $2 million, we had to present about $2 million worth of paper. Now, I say we because I used to be, before I joined Google, I was part of that group in Europe. So number one, to facilitate experimentation with programming languages. So the standard implementations of Python are written in C, Java, C#. So to experiment to make a different language that's similar to Python, you basically have to know beyond Python also C or C# or Java. With PyPy, you can do your experimentation Python itself, so it's easier to experiment. And even if you do know, we claim that Python makes you more productive. So even if you do know the other language, you should be able to do your experimentation twice as fast if you can do everything in Python. Also, freeing the backend from the specific constraints existing in the existing implementation, basically by coding the output, so to speak, to an abstract backend which is suitable for compilation to either higher level bytecode engines or machine code, basically frees up to do a lot of backend. If you look at PyPy 1.0 as released, it's got a funny collection of backends. For example, it has a backend which compiles Python to JavaScript. The reason are obvious. You can pump that on the, put that somehow as part of your web pages and basically do the logic behind your web pages on the user's browser, but in Python. There's an the one backend generates common Lisp, which then has some pretty strong compilers around, mostly commercial ones. Other implementation generate machine code. That's not very satisfactory to me, so bloated. It generates not very efficient machine code. Another one generates code for something called the LLVM, the low-level virtual machine. You should read up on that on the web. So basically, it's got a lot of backends because it can. It's designed to have multiple backends. And part of what it does have to enable specifically the easy generation of machine code or the equivalent of machine code, it's got type inference built in. So we don't really need that to generate JavaScript or common Lisp, but it's still handy. And it's particularly handy if you want to generate machine code, even though it comes out very bloated. You need to know whether something is an integer or float because it may occupy a different number of bytes in memory. So, any other? Yes?
Can you go back to page 23 or 24?
I presumably can, although it will take a while. Oh, actually, it self-repeats. Cool. Well, only for a while. Which one? 21?
Next one,
23?
Yeah, so I don't see the advantage of generator. So some function's going to call enumerate to pass in a sequence, and this is going to return one item. So why not?
Yeah, it's gonna yield one item and suspend. The next time is gonna yield the next item. So take one example of enumerate that I have. Ding, ding. When I do the indexing example, I'm using enumerate. There you go. So enumerate is called once. But then we loop on it. So we get 0 in the first line, 1 in the second line, 2 in the third line. So we're getting the line number as well as the line as we go, without having to deal ourselves with low-level logic such as n equals 0 and n plus equal 1. Well, that's what enumerate does for us.
If you iterate over your sequence in that same folder,
If I iterate over my sequence, I don't get the line number. I get the lines, but I don't know what line number I am, and I need to save the line numbers by problem definition. Yes?
So there were two syntaxes for calling a super method,
Mm-hmm.
a method called super. So why, when we use the keyword super, we need to pass the self, but when we use the parent class, there is no need to pass the self.
There is. It just passed in a slightly different syntactic position, but it is definitely passed. See? You have to pass it explicitly to the method because you're calling the method on the class, while this basically wraps it up so it gives you a virtual instance of your superclass. So you're calling a method on an instance which implicitly passes itself. Yes?
Towards the end of the talk, you indicated that setting global variables towards the top, for example.
Setting what, sorry?
Global variables towards the top of the script is not considered good form.
It's fine. I'm just saying that in the example I was giving, there's absolutely no use of that variable until much later, so why should I set it?
Well, I was looking at more from a maintenance point of view. There's a lot of our Python scripts that we work with in CPV are several thousand lines long. Do you have any preferred style?
Yes, make them smaller. You're welcome. If you don't have control over the source code, then you will take whatever source code you're given. But if you do have them, then insist on making them a reasonable length. There's really no reason to do otherwise. You can tell me you have no control to split them down into reasonable length, say a couple hundred lines at most, but you can control which 200 lines they are. That doesn't make sense. If I did have to maintain a 1,000-line script, I probably would refuse to use any global variables at all. I would wrap everything into classes. So if I can't have a decent source code control that way, I can't. How many people will be editing a 1,000-line file at a time? I can just see the conflicts in your source code control system and people resolving conflicts by hand all the time. It's going to be hell. So anyway, at least the conflicts will be in different classes with any luck. I think we have one more question.
I was curious if there was anything similar to the use strict directive in Perl.
No.
Do
There
you
isn't.
have a lot of errors just caused by typos?
There isn't. There are tools such as PyChecker, which will catch all your typos, but they're completely separate from Python. You don't load them separately. Yes?
Are there portability problem between the Python implementation going from .NET to
Okay, not for the language, but the libraries are not identical. So you have to realize that the main motivation for somebody to port Python to .NET was to make available Windows forms. If you do use them, don't expect that you run the same script on Mono under Linux, Windows form will appear. They won't. They're Microsoft crown jewels. So essentially, the language is totally portable, but you never do anything with the language alone. You're always calling some library or other. Be careful which library you call, because if you call a proprietary library that only exists on this platform, well, then, you know, say you're using SQL as part of your Python script. If you're developing for Microsoft SQL using all of its specific dialects and features, then moving to Oracle will be hell, but it's not Python's problem. It's your problem. Yes?
I have another question regarding this yield method.
The what method?
A function with yield.
Yes,
What, for example,
generators.
if we have a function with yield, and we have like a multi-threaded program, and we both threads simultaneously call this function with different sequence.
Okay, when you call the function returns an object. So if two threads call the function, you get two separate objects, no interference.
And we call next on this object.
Every time you call next, you consume an item. No matter how thread safe you can make it internally, you will still be consuming one item. So if there will be a race condition for calling next between the two threads, that's assuming the inner body is safe between successive yields being simultaneously in execution, so you're going to get some non-deterministic effect. Sometimes the first thread will get the first two items, and then a couple for the other, and then by other times different interleavings.
Yes, I understand it.
It's kind of like, what if the thread spot did print on standard output? Well, the lines coming from one and the lines coming from the other would be mixed in about randomly.
No, I understand this, but I don't understand something else.
Mm-hmm.
How we know, for example, if we call this method twice with two different sequences?
If we call it twice, then we get two different objects,
Yeah, but
which don't interfere with each other.
Isn't method basically just one object, which was defined when method was basically, when it was defined?
I don't understand what you're saying.
We have a method which is defined with def statement.
Okay.
Okay, when in runtime, when this def statement is executed, an object is basically,
A function object is created.
yeah, a function object
Yes.
is created. Then when we call a method, we basically we use this function object.
Mm-hmm.
And
If that contains a yield, then it's the generator,
Yeah.
and what it returns is an iterator object. What it returns when you call it is an iterator object.
So it returns an iterator object, and then
Yes.
you call next an iterator object.
Exactly.
Okay, thank you.
Thank you very much. I think it's getting a bit late, so we should be going.